There's also, unfortunately, fortunately, a bookish way to do that. That is what uses the reverse. So I will have to tell you that as well using reverse. So let's write down reverse the way I like it. So I need to write down reverse of the list L produces the list L1. I love drawing things. So this time I'll have to unfortunately write down some A, B, C, D, E. Previously it was okay because I could just say visualize this list as here. Now it's reversing, so I'll have to do something. So that's my list L. Of course, this is head and this is my tail. I'll recurse on this. And it produces my output list, which is FEDCBA. That will be my output list. That's my L1. So what do I of course do is that I first reverse T, which will give me a FEDCB, and then I say reverse T gives me a T1, and that's step 1. And step 2 is at end. In the list T1, I add H at the end. So that gives me my answer. That gives me my answer. And of course, this will be written as reverse of T gives me a T1. So let's write it down. So I say that's reverse version 1 of L1, L broken down as head and tail. It, of course, is given by step number 1. I reverse T to produce the reversed list T1. Step number 2, I say add at end. To the list T1, I add H at the end to get my actual list L1. So let's check reverse version 1. Oops. So that's reverse 1, and my base condition is reverse of an empty list is empty. So 1, 2, 3, 4, 5 reverse, it of course gives me 5, 4, 3, 2, 1. So let's quickly go down to our old part program. So it worked like this. I'm rubbing in all the changes. I was adding goal on top of a V. And here, of course, I did not add it at the end. I said it is X added on top of V. So let's again do it. I say path from A to E. Using the visited set, only A is visited and the path P. Oops, of course. So I get the correct thing, but it's instead of ABCE, I get ECBA. Instead of ABCE, I get the part which is exactly the inverse, which is EBCA. And now, therefore, I need to reverse it up. So I get, say, this is some temporary part P2, and my part P is nothing but what is the output of reversing P2. And let's run that up. Oops, it's reverse version 1. So yeah, my answer, which is P, is ABCE. ABCE. You could just go around and get all the others. So it's also ABDE and it's also ACE. Unfortunately, again, there is a trick, and the book, I mean, as in many people use that little trick. I'm not a very much fan of this little trick, but then if there is a trick, you might just use it. So let's go down onto let's go down onto a list which is A, B, C, D, and let's reverse it up. So I say reverse of L, which is ABCE, produces the list L2. So reverse of ABCD, it produces L2. How could I satisfy it? Let's just travel from head to tail. So that's the simple traversal that you could have even into Prolog. So I divide it up into head and tail, and from it I call reverse head left alone and tail, which is a BCD with some L2, head left alone. So let me write down the heads as well over here. So here A was the head, here B was the head, and then reverse CD with some L2. Then again C was the head, left alone, reverse D with some L2, and again let D be left alone, so it's reverse empty list, and you cannot do anything with some L2. So I'm just doing a normal traversal of a list. Now the thing is that you need to reverse it up. So whatever I was leaving around, let's keep on adding it to a temporary auxiliary variable. So I say temporary auxiliary variable T, initially empty. So when I make this recursion, I add whatever I was leaving, I added to the temporary auxiliary variable. B, I added up front of the temporary auxiliary variable. C, I added up on top of the temporary auxiliary variable. D, I add up on top of the temporary auxiliary variable. And finally, I say answer is equal to my temporary auxiliary variable. So my answer is whatever is the value of this temporary auxiliary variable. I won't go into much detail of that. I'll just define that up. I'm not a great fan of this technique, honestly. It's just that people like to use it. So reverse version 2, the reverse of the list L, which is a head and a tail, with some variable which is auxiliary, produces the list L2. So what do? I just recursively traverse the list. So I call the recursion of head left alone on tail, and I add head on top of the temporary auxiliary variable T, and L2 is my answer. Now what happens is I actually get my answer at the base condition. So base condition, when my list is empty, my temporary auxiliary variable T, and my answer is nothing but whatever was there in my temporary auxiliary variable T. So I'd say answer is equal to temporary auxiliary variable T. So I would have said L2, and L2 is equal to T. I just coded directly over here. So let's try this out. Reverse of 1, 2, 3, 4, 5 produces L. It's a reverse 2. Oops. Auxiliary variable, nothing. Oops. Let me quickly check it. Reverse tube of nothing. The answer is what is a T, and of course, if I have a head and a T, and oh my god, why did I use T two times? So let's say A is the auxiliary variable. So I recurse on head and I say my H added on the auxiliary variable. So yeah, 5 4 3 2 1 1 2 3 5 5 4 3 2 1. That's also the one, and of course you could use exactly the same thing into what you said and the answer will come out. If you want that, I mean, as of now we are returning path, not the distance. So if you say what's the path from A to E using the auxiliary, I mean using the visited as A, the path as P2, and of course I will use reverse of P2 to get my actual path P. You see that it returns correct ABCE, but it doesn't return the distance. So how do I return the distance? I say, is there a path from source to goal with visited as V? So effectively only two are the inputs and the rest are coming out to be auxiliary. Path P, which has a distance of D. So let's add this D up in everything. So this only holds good when the distance is 1. It only holds good when the distance is 1. So I have my value of D as 1. And here a path exists from S to G with a distance of D if a edge exists from X to X, and a path exists from X to G whose distance is D minus 1. And remember, I cannot do arithmetic over here. So I say whose distance is D1, where D1 is D minus 1. Now, that's pretty interesting for multiple reasons. Let's check it out first. So I want the path as well. There you go. So happens that even though logically this may appear to be doing exactly as you want it, so even though it may appear that it's doing exactly as you want it, but it does not come out because I cannot do n and arbitrarily arithmetic. Now, let's see, and in this case, I of course have to do an arbitrary arithmetic. Now, let's see what will happen is, finally, some substitution of 1 will happen. So I can do an arithmetic where it is D and it adds on top of it. So I can do the additions, I cannot do the subtractions. So I can do a plus. So I say D1 is plus, and of course mathematically these two are equal. What will happen is that the value of D1 after a few substitution, D1 will become 1. Now because D1 will become 1, so 1 plus 1 is not an arbitrary arithmetic. 1 plus 1 is equal to 2, both satisfied. 1 by substitution right at the end and 1 by a plus 1. I actually know that. So I get my D. And it's recursive. So once I get my D, that D was somebody's D1. So 2 is there. 1 is also there. So you get 2 plus 1, which is a 3. Oops. Okay, it does turn out that in order to say that yes, this is bound by this substitution and all, I'll first have to calculate D1 and then get the bounded value. So singleton D and D1. So D is D1 plus 1. Okay, that has to be a comma. Yeah, so there is a path of length 3 that goes A, B, C, E. Let's check it out. So A, B, C, E. Yes, the path length is 1, 2, 3. There's also A, B, D, E, which is a path length of 3, and then 2, which is A, C, E. A, C, E. I could have done it the other way, like calculating really the length of the visited, and that would have also given that to me, or calculating the length of the path that would have given it to me. I like to unnecessarily incur errors and then just get out of it. Now, you saw that we were trying to calculate the distance, and all that we did was to calculate that up. Now, it so turns out that can I say D is equal to 2 is my interest, A, C, and E. And yes, so I asked the question, is there a path of length 2 from A to E with the visited, of course, initially only A, and P is what I need as my path? The answer comes out to be correct. It's A, C, and E. That's the optimal path. I do it the other way around. Is there something with a 1? False. No, sorry. Is there something with a 3? Yes, there's 1 and there's 2. Two paths with a length of 3. Is there one with a 4? No, false. You may think because it's cycle it will be there, but then we have the visited constraint. And now using this, can I have something like an iterative deepening which will go on smaller values first and try out? So let's try to see if we can get that. So I say iterative deepening. So I need to get a path from the source S to the goal G with the current limit as L. And all that I do is I first try to, and of course the path will be returned as P. If you want, you can also return the distance. So I first check out from the source to the goal. Is there a path with only the source initially in the visited? And if there is a path, let that be stored in the variable p2. However, I am only looking in for paths which have a distance of exactly L. And if I do get a path, wonderful. Just return P is equal to reverse of P2 or reverse P comma P2. However, if you don't get it, it's semicolon, so that is a or. If you cannot do it, then go on iterative deepening on from the same source to the same goal L using the limit as L plus 1, which is L1, and of course the path will be returned as P. So I say L1 is L plus 1. So let's see if I can do that. Can I do a iterative deepening from A to E using a limit initially starting off with a 1 and the path as P? A, B, C, D, A, B, C, D, A, B, C, D, A, B, C, D. I hope the spellings are all correct. So, spelling mistake. So, I say that iterative deepening, I go level by level. So that's my first answer. And of course, iterative deepening, it will keep on going around. So what you can do is iterative deepening, ideally also if you supply something which is not possible a fail. The real iterative deepening will not return a solution. It will keep on trying level 0, 1, 2, 3, 4, 5. So what you could do is that you could also set a limit on L1, let's say 25, go on maximum 25. So is there a path from A to E? Yes, it is ACE. And is there one from BA? False, there's no such path. It's because I now applied in a limit, and the limit is really ensuring that whatever happens. So I'll not do it for the others, like BFS. You take, instead of a visited queue, and then you add, basically your new queue given recursively is your old queue plus the new ones that you have generated. But one thing that I will of course do is that so far we have defined graphs as A, B, C, D, E. So let's just define a graph in terms of state. So very quickly, my actual grid search problem, where I had to go from some node to some other node with some obstacle, source, goal, whatever. So the maximum difficulty was to make a transition system. So I say transition between the cell S, which has some I or J. So that's a state. And that's a structure, a combination of I and J. It gives me a new state, I1, J1, such that, so when you go up, I reduces. I1 is I minus 1, and J1 of course remains the same, so I could just write it down as a J. So that's the transition for the function up. Let's quickly check that up. So I say trans up is just a symbol, it's not upper caps that it'll be something. And I need to go up from the cell 2, 3. It gives me the state X. So X is of course 1, 3. From 2, 3, if you go up, you go to 1, 3. Of course, the problem is from 0, 3, if I go up, I go to minus 1, 3. That's not allowed. So I do add that as a constraint, that I1 should be greater than equal to 0. So false. There's no such X. You cannot go. Let's do it quickly for all of them. So down is of course +1, and this should be less than the map size, let's say 25. Left is so the J reduces, I remains as it is, and J1 should be greater than equal to 0, and let us say right is J1 +1, and J1 should be less than equal to 25. So very quickly, let's apply these up. Oops, so it's singleton. So left is IJ produces a IJ1, where J1 is J minus 1 and J plus 1. Yeah, so from 3, 3, let's go all direction. Right and left. So I get all my transitions as simple as that. So I get in all my transitions using this thing around over here, and that's exactly what you could use in as the transition function in any one of the searches as we have. defined it up already. Now, fortunately, what is it that you can do something more than that? I say I apply any action on tree tree. What does it lead me to? So if I apply up, it leads me to 2 tree. If I apply down, it leads me to 4 tree. If I apply left, it leads me to tree 2. And if I apply right, it leads me to tree 4. So that's more or less like your link function. And this was where I started off by saying A, what does it all lead to and what all leads to A. You could also do it the other way around, of course. So I've now defined in more or less my same graph in a slightly newer format by this transition function. And the moment I define it as a transition function, this transition function that you have now in a logical Prolog format becomes now your new equivalent of the edge function previously defined on state spaces like this. So everything will go on state spaces. And using that, you could do whatever we have been doing so far. So to end up the discussion, Prolog, of course, because of the coronavirus, I have taken it up with a few examples. Otherwise, in this university, technology, application, and programming, we directly give it to you as assignments and you do it, and we meet in the examination where you attempt that up. My mantra will be that do not follow whatever I have done. Just take in as many questions as you can make it for yourself and solve it on your own. So when you make mistakes, that is when you reason about what really did we go wrong on. And then when you correct yourself, that has the maximum learning. And that's why my figures were shabby. I didn't even want to write down something. It's because I want you people to practice it up rather than me giving you any straight solution. So practice as hard as possible. It's still a lab where you learn the maximum yourself. And for now, it's already late over here. So that will be all for the day. Thank you.